Hi guys, welcome back. So today I have a fresh set of exponential equations, 4 problems to be exact. But before we knock out our first fun problem, let's go ahead quickly review what we did in the earlier video. Okay, so we were solving exponential equations. So to recap, what's an exponential equation? An exponential equation is pretty much an equation that has a variable in the exponent. Cool. Now, to solve these exponential equations, ideally we want to fix it so the bases are the same. We want to fix it so the base on the left equals base on the right. And if that's the case, then we apply the property of exponential equations. So remember, the property of exponential equations says this: if the bases are equal, then there's no way around it. Then the powers have to be equal. So let's go ahead and knock out our first problem. Then we'll have 3 more and then we're out. Okay. So I'm like, okay, problem A, we are asked to solve this bad boy. So when it comes to solving equations, I always have to ask myself, what kind of equation is it? Is it a linear, quadratic, rational, radical, or in this case, exponential equation? So to answer that question, I kind of like to look at the variable. I notice where the variable or variable terms are located. The variable terms are located in the exponent area, so we have an exponential equation. So now that we have that out of the way, now that we have identified that type of equation, now we can make a strategy. So I'm like, okay, how do we solve an exponential equation? So ideally, we want to fix it so the left and right side are written in terms of the same base. Sometimes we can fix it so the left and right side are in terms of the same base. Sometimes we cannot. The cannot part will come in a later video. Okay, so I'm looking at the left side. So we got a base 9. So I'm like, oh, should we aim for base 9? Maybe. But last time I checked, we cannot write 27 in terms of base 9. Or in semi-English, we cannot write 27 as a power of 9. But if we were to prime factor 9, we would realize that we get a couple of 3s. So last time I checked, 9 is the same as 3 times 3. Okay, so we can write 9 in terms of base 3. And check it out, we can also write 27 in terms of base 3. So why don't we aim for base 3? Okay, so when we solve exponential equations, the first thing I want to ask myself is this: can I fix it so the left and right side are written in terms of the same base? And if so, what am I going to aim for? So I'm like, okay, let's aim for base 3. So when we write 9 in terms of base 3 or power of 3, we have that 9 is the same as 3 times 3 or 3 squared. So let's do this. So we have 3 squared. What's going on with that 9? Oh, it's being raised to the 2x minus 8 power. So let's go ahead and raise it to the 2x minus 8 power. Equals, let's go ahead write the right side in terms of base 3. So 27 is the same as 3 times 3 times 3 or 3 to the 3rd power. So let's go ahead and do this. That will give us 3 to the 3rd power. And then I'm like, okay, what was going on with that 27? I mean, what is going on with the 27? The 27 is being raised to the x minus 4 power. Fantastic. So we have 3's on the left and right side, but it's not quite base 3. The base on the left is 3 squared and the base on the right is 3 cubed. It's not base 3. Okay, so what are we gonna do? We're gonna go ahead and use the power rule to simplify both the left and right side. So where do I have space? So a gentle reminder, the power rule says this: if we have a factor and we raise it to some power, how do we simplify it? Okay, we're going to keep the base and then we're going to multiply the exponents. Okay, so go ahead and review that video from an earlier chapter. Okay, so let's apply the power rule on the left. How are we going to fix it? Raising powers, we're going to keep the base and then we're going to multiply the exponent. So that will give us 3 raised to the 2x minus 8. Okay, we have power rule on the left. Let's apply the power rule on the right. Power rule on the right side, raising powers, we're going to keep the base of 3 and then we're going to multiply the exponents. Cool. So remember, our first goal is to fix it so both the base on the left and base on the right match. At this point, we're going to apply the property of exponential equation. So remember, the property of exponential equation says this: if the bases are equal, then there's no way around it. The powers have to be equal. Okay, more thinking area. Okay, so in this case, if the bases are equal, then there's no way around it. Then the powers have to be equal. So let's go ahead, set the left exponent equal to the right exponent. Left exponent equals right exponent. Now, what are we going to do at this point? At this point, you're going to solve the resulting equation. So let's go ahead, clear the grouping symbols, and then we'll make that strategy. When we distribute the 2 on the left, that will give us 4x minus 16. When we distribute the 3 on the right, that will leave us with 3x minus 12. Okay. Now that the grouping symbols are gone, it's a little bit easier for me to make the call of how are we going to attack this new bad boy. So the degree is 1, so we have a linear equation. So let's old school it. We want variables on one side, non-variables on the other. If I can read your mind, we're going to go ahead, subtract 3x from both sides. And if that's not you, it's okay. Signs will cancel, and I promise we'll get the same answer. So if we choose to subtract 3x from both sides, that will leave us with x minus 16 is equal to negative 12. Okay, so we have variables on one side. Let's go ahead, isolate it at this point. To undo the subtraction by 16, let's go ahead, add it to both sides. If you want to impress your friends, you're like, oh, let's do the inverse operation. Okay, yeah, whatever. Okay, so after we add 16 to both sides, that will leave us with x equals, I think it's 4. Okay, and then I check this at my house. Cool. Alright, so we have one problem down. We got 3 more to go. Okay, problem B, where am I? Problem B, we have 25 raised to the 4x plus 3 power is equal to 125 raised to the 2x minus 3 power. Fantastic. Okay. So again, first thing we want to ask ourselves is this: what kind of equation is this? And pretend I did that entire checklist. So I'm like, okay, the variable or the variable terms are located in the exponent area, so we have an exponential equation. How do we solve exponential equations? We are hoping that we can fix it so both the left side and the right side are written in terms of the same base. When I look at 25, I'm thinking, oh, base 25, but we cannot rewrite 125 in terms of base 25. But I know that you know that 25 is a power of 5, and ditto for 125. So let's go ahead, fix it so both the base on the left and base on the right are written in terms of base 5. Okay, in semi-English, fix it so the left side and right side we have powers of 5. So when we break down the 25, if we prime factor it, we realize that 25 is the same as 5 times 5, so we have 5 squared. Now, what is going on with the 25? Oh, we're raising it to the 4x plus 3 power. So we don't have quite base 5 on the left, it's base 5 squared, but we're getting there. We have 5s on the board. 125, when we prime factor it, we realize that's the same as 5 times 5 times 5, or 5 cubed. Okay, 5 to the 3rd power. What's going on with the 125? It's being raised to the 2x minus 3 power. Okay, so at this point, let's go ahead and use the power rule for exponents. So remember, power rule for exponents, how are we going to do that? We're going to keep the base and then multiply the exponents. Keep the base, multiply the exponents. Power rule on the right. Okay, we're going to keep the base and then multiply the exponents. Before we proceed to our next step, let's see if we satisfied our first goal, which is fix it so both the left and the right side are written in terms of the same base. In this case, it's 5. We got base 5 on the left, we got base 5 on the right. So let's do this. So at this point, we have the green light to apply the property of exponential equations. So remember, the property of exponential equations says this: if the bases are equal, then there's no way around it, and the powers have to be equal. Okay, so let's go ahead, set the exponents equal to each other. So left exponent equals right exponent. Let's take our time, clear those grouping symbols, and then make the call of how to solve this new equation. When we distribute the 2, that will leave us with 8x plus 6. We take our time and distribute the 3, and that will leave us with 6x minus 9. I forget to say the following, but don't forget, pause and rewind as many times as needed. Cool. Now that the grouping symbols are gone, it's a little bit easier, or a lot easier, for me to make the call of how to solve this new equation. The degree is 1, exponent is 1, so it's a linear equation. Let's old school it. We want variables on one side and then constants on the other. If I can read your mind, let's go ahead, subtract 6x from both sides. What if that's not you? It's okay, we'll get the same answer. Okay, signs will cancel and we'll get the same answer, I promise. After we subtract 6x from both sides, that will leave us with 2x plus 6 is equal to negative 9. Okay, following the procedure, work your magic to isolate the variable term. If you're not with the variable term, you gotta go. Inverse operation of addition is subtraction, or in English, to undo an addition, let's go ahead and subtract it, and that will give us 2x equals negative 15. At this point, I'm having a moment because I realize that our answer is not going to be an integer, and that's okay. I think we are falsely trained to believe that our answers have to be integers, but they don't. Okay, so go ahead, work your magic. To get rid of the times 2, let's go ahead, divide both sides by 2, and that will leave us with x equals any equivalent form of negative 15 halves. I check my answer at the house. Okay, so the question is, do you have to write it as a mixed number? No. Can you write it but can you? Yeah. Can you write it as a decimal? Yeah. I myself will leave it as a fraction because sometimes my fingers slip and I tend to put the wrong button on the calculators. But yeah, so decimals are fine, just make sure you don't round. Okay, I'm gonna look for a third problem. Give me a sec. Alright, so the third problem has been identified. Remember, we're doing a total of 4, and don't forget, pause and rewind as many times as needed. So we have 100 is equal to 3x plus 7. Say that again. We have 100 raised to the 3x plus 7 is equal to 0.001 or 1,000. Okay, so then I'm like, okay, what kind of equation is this? We notice that the variable is once again, surprise, in the exponent area, so we have an exponential equation. So how are we going to handle it? Our first goal is to fix it so both the base on the left and base on the right are the same. So in short, fix it so the bases are the same. Now, if we were to prime factor the 100, we will get 2 different factors. Unlike the other problems, it's not going to be one factored multiplied over and over again. Okay, but I know that you know that 100, we can write it in terms of base 10. Okay, now this I'm not exactly sure where we're going with, so what I'm gonna do, I'm gonna write it as a fraction. Maybe if I write it as a fraction, I'll see it. Okay, so we have the left side, we're just gonna keep it as is for now, is equal to the right side in fraction form. So for me, I'm gonna go ahead put the fraction bar first. It was always difficult for me to write the decimals in fraction form, but this is how we're gonna handle it. We're gonna look at the place value of the last digit. So we have tens, hundreds, thousands. So the last digit is in the thousands place, so the denominator should be 1,000. Now the question is, how many thousands do we have? Just 1. Okay, so the decimal digits will be the numerator. So no matter how you write it, whether in decimal form or in fraction form, they're both read as 1,000. So now the question is exponential equations. Our first goal is to fix it so both the left and right side are written in terms of the same base. Base on the left is 100, and I don't think we can write this 1,000 as a power of 100. But 100, I think we can write it in terms of base 10. And if I keep my cool, I think 1,000 is also in terms of base 10. I'm thinking like difference the squares. 100 is a perfect square because it's the square of 10. 1,000 is a perfect cube because it's the cube of 10. So something 10, something 10. We're going to go ahead aim for base 10. Fantastic. Someone said, why do I do squigglies? Because I'm thinking. Okay, that's my thinking area, like in the comic strips. Okay, so for this exponential equation, again, we want to fix it so both the base on the left and base on the right are written in terms of the same base. And in this case, we're aiming for base 10. When we keep our cool and we rewrite, I need to pause myself. When we keep our cool and rewrite 100 in terms of base 10 or powers of 10, that will leave us with 10 squared. And the question is, what is going on with this 100? Well, that 100 is being raised to the 3x plus 7. Now, am I having a moment because of the fraction? I sure am. But you know what? We're just going to take this one step at a time. Okay, so we have 1 over 1,000 in terms of base 10 or power of 10 is the same as 10 to the third powers. So we have 10s on the board. We have 10s on the left and right, but it's not quite base 10. Okay, so on the left side, let's go ahead, use the power rule. And if you need a reminder, here you go. Okay, so power rule. If you have a factor and you're raising it to some power, how are you going to handle it? You're going to keep the base and multiply the exponents. Okay, so power rule on the left, keep the base of 10, and then you're going to multiply the exponents. On the right side, we have a 10, but it's not quite in the place where we want it. We want the right side also to read 10 to some power, not 1 over 10 to some power. So we're going to use the negative exponent rule in reverse. So I forgot to write it in the earlier videos, but when we talked about the negative exponent rule, the question is, how do we fix it so the exponent is positive? So to do that, you're just going to move the factor about the other side of the fraction bar. So if there's no fraction bar, we make it up. Okay, we bring the factor to the other side. In this case, bring it down. And anytime you move a factor to the other side, you're going to switch out the exponent. So if the exponent was negative m, and you switch out the sign, it's positive m. Okay, so pretty much we're going to use the negative exponent rule in reverse. Okay, so we are bringing the 10 to the other side, not because the exponent is negative. As you can see, it is not negative, but we're bringing it to the other side because we want 10 to some power. Again, we don't want the 1 over 10 to some power. So we switch this, shift the 10 to the other side. And again, anytime you move the factor to the other side of the fraction bar, you got to switch out the exponent. So before the exponent was positive 3, just kidding. Now it's going to be negative 3. Okay, what happened to that 1? Well, 10 to the negative third multiplied by 1 is still that. Okay, so don't think I just ignored it. Okay, to solve exponential equations, our first goal is to fix it so both the left side and right side are written in terms of our first goal is to fix it so both the left side and right side are written in terms of the same base. We got base 10 on the left, we got base 10 on the right, so let's do this. So at this point, let's go ahead and apply the exponential property of equations. I think I said that wrong. Okay, let's go ahead and apply the property of exponential equations. So the property of exponential equation says this: if the bases are equal, then there's no way around it. The powers have to be equal. Okay, so the left exponent should equal the right exponent. Let's go ahead and do that. Left exponent should equal the right exponent. Let's clear the grouping symbols and then make a strategy of what to do to solve it. When we distribute the 2, that will give you 6x plus 14 is equal to negative 3. Okay, we got a degree 1 equation. Surprise, we got a degree 1 equation, so let's go ahead and solve it. So we want variables on one side and everything else on the other. To undo the addition, let's go ahead and subtract it. When we take our time and subtract 14 from both sides, that will leave us with 6x equals negative 17. Again, am I having a moment because our answer is not going to be an integer? No, fractions are fine. Okay, to isolate the x, to get rid of the times 6, let's go ahead and divide both sides by 6. And when we do, that will give us that x equals any equivalent form of negative 17 over 6. You can do a mixed number or decimal, but just make sure you don't round them. For the grand finale, problem D. Okay, problem D, we have 4/3 raised to the x power is equal to 27 over 64. Okay, 4/3 raised to the x power equals 27 over 64. So I'm like, okay, this is a funny problem, but it's okay. That's why it's problem D. On the left side, we have a fraction. The base is 4/3. I'm like, should we write the base a little bit differently? No, I think it's fine. Like 3 is a prime number, so it's going to be in terms of base 3. 4 is not a prime number, so our options are to write it in terms of base 4. or maybe base 2. But I wouldn't recommend you do base 2, because if you do base 2, it's going to be 2 to the second power, and 3 is not being raised to the second power. So we'll just aim for base 4/3, okay? So let me go ahead and write base equals 4/3, but I'm having a moment, so I don't really know if it's really possible. So we're going to break it down. And when we say that the base is 4/3, let's two-step it. We want the numerator to be base 4 and the denominator to be base 3. So I'm like, on the right side, can I fix it so we have base 4/3? 27 is not a power of 4, but I know that 27 is a power of 3, so we could totally do base 3. It's just in the wrong place, okay? I'm like, the bottom, can I write it in terms of base 3? No, but we can write 64 in terms of base 4, but it's just in the wrong place, okay? I don't know if I contradicted myself, but let me start writing, okay? So we could totally fix it so we have a base 4 on the top and a base 3 on the bottom. So let's do this. The left side, we're going to bring it as is. Now we're going to take our time and fix it so we have base 4 on the top, base 4 on the bottom. We had already said that 27, we cannot write it in terms of base 4, but we're going to write it in terms of base 3. So when we keep our cool and prime factor it, we have that 27 is the same as 3 times 3 times 3. So give us 3 to the third power. 64, if we were to prime factor it, we would have a handful of 2's, but we're not going to prime factor it. We're just going to ask ourselves, can we fix it so it's written in terms of base 4? And I think so, okay, because I think 64 is a perfect cube. Let's put it into the calculator. 4 times 4 times 4, I will leave that 64. Okay, someone punch it in. So we got a 4 in there, we got a base 4 in there, we got a base 3 in there. They're not quite where we want them to be, but it's very easy to flip them, okay? Now, in this case, let's go ahead, just fix it so both the 3 and 4 are both being raised to the third power, okay? So we're pretty much going to apply the power rule in reverse. So instead of both the 3 and 4 individually being raised to the third power, we're going to take the quotient or the fraction and raise it to the third power. So if we were to evaluate this, this will give us 3 to the third power, just like we have, and 4 to the third power. So we're not changing anything. So now we have a base 4 in there and we have a base 3 in there, but it's not quite like the same, okay? So let's go ahead and use exponent rule, the negative exponent rule in reverse, okay? So pretty much we're gonna flip it, okay? So when anytime you move the factor to the other side, so in this case we bring the top to the bottom and the bottom to the top, then that will give us anytime you move a factor to the other side, we're gonna go ahead and switch out the exponent, okay? But I think I should have explained this a little bit differently. Let me go ahead solve this and then I'll give you a different explanation. Let's see which one works for you, okay? So now the question is, did we fix it so the base on the left is the same as the base on the right? We have base 4/3 on the left, base 4/3 on the right. Now at this point, since the bases are the same, we can apply the property of exponential equations. The property of exponential equations for the fourth and final time says this: if the bases are equal, then there's no way around it, and the powers have to be equal. So the left exponent equals the right exponent. So I'm not quite sure if I conveyed what I wanted to say with this problem, because I'm having a moment. So let me do an alternative solution. Okay, so let me put SOL in for my made-up abbreviation for solution. I think this solution will be a little bit easier to digest. Okay, so we want to fix it so we have base 4/3. So if we break it down, we want the base 4 on the top and the base 3 on the bottom. So we got the 3 and the 4, but in the wrong place. So let's go ahead, move it. Okay, when we apply the negative exponent rule to the numerator, let's go ahead, bring it down, and then we'll switch out the exponent. We're going to apply the negative exponent rule in reverse to the denominator, bring it to the other side, and then switch out the exponent. Okay, so we have 4/3 raised to the x power equals, okay, we bring the top to the bottom, and then we switch out the exponent. We bring the bottom to the top and then switch out the exponent. So at this point we got a 4 on top, 3 on bottom, but I want base 4/3, okay? I'm very thankful that both of these are being raised to the same power, so let's use the power rule in reverse to write it as the quotient raised to the -3. So we have 4/3 raised to the x power equals 4/3 raised to the -3rd power. Okay, so it goes to show there's more than one way to skin a cat. I think that's the saying in English. Cool. And if you're having a moment, try to evaluate it and see if you get the same thing. 4 to the -3rd power, yeah, 4 to the -3rd power. 3 to the -3rd power, that's exactly what we have. Cool. So now the question is, did we fix it so the bases are the same? And the answer is yes. So remember, if the bases are equal, then there's no way around it. The powers have to be equal. Okay, so the left exponent equals the right exponent. Once again, the variable is isolated, so there's nothing else to do. Okay guys, so I said we were gonna do 4 problems. That was our 4th and final problem. And if you don't hear me like with the enthusiasm, it's because I'm tired. Okay guys, bye.